Okay, good morning, good afternoon, and good night to everybody. Today we'll discuss about sound waves and Doppler effect. Actually, this is the last chapter, and we'll focus on actually Doppler effect. First of all, we review the sound waves. First of all, we'll review the sound wave. First of all, what is sound? The nature of sound, ears and speakers. And sound is really tiny fluctuation of air pressure, and units of pressure Newton per meter square or psi, and carried through air at 345 meter per second. That means velocity of sound in air, and 770 mile per hour as compressions and rarefactions in air pressure. This is the actual longitudinal wave and compression, and this is the rarefaction, and this is the compression, and this is the rarefaction. This occurs due to the pressure of compression. So distance between two compression or distance between two rarefaction is called wavelength. This is the compression and this is the rarefaction. That means density big, high density makes compression and low density make rarefaction. What's the properties of sound wave? Actually, we must know wavelength is measured from crest to crest or trough to trough or upwing to upwing, etc. That means this is the wavelength. And to complete making of this wavelength is called time period, capital T. For traveling waves, sound, light or water, there is a speed C. Frequency F refers to how many cycles passes per second, measured in hertz, and T equals to capital T, that means time period equals to 1 by frequency. And these three are closely related. C equals to F lambda or B equals to F lambda in other books. So there are two waves, longitudinal versus transverse. Sound is longitudinal wave, meaning that the main motion of particle is along the direction of propagation. And transverse waves, water waves, light waves have things moving perpendicular to the direction of the propagation, making densely and rare. That means compression and rarefaction moving along the wave. So why sound longitudinal? Actually, this is a great question for us. Waves in air cannot really be transverse because the atoms and molecules are not bound to each other. Can't pull a momentarily neighboring molecule sideways. Only if a rubber band connected the molecules would this work. Fancy way of saying these gas cannot support shear loads. So air molecules can really only bump into the another. Imagine people in a crowded train station with hands in pockets. So pushing into crowd would send a wave of compression into the crowd in the direction of push, longitudinal, jerking people back and forth sideways over several meters would not propagate into the crowd. But if everyone held hands bonds, this transverse motion would propagate into crowds. This is the real life example to understand why sound is longitudinal. The sound wave interference and beats. When two sound waves are present, the superposition leads to interference. By this we mean that constructive and destructive addition. Two similar frequencies produce beats, spends a little while a phase and a little while out of phase. result is weighting of sound amplitudes. So in phase weight, this is the single A and signal B, and this is the signal A plus B. That means interference occurs, beat, out of phase cancel. Okay. Now speed of sound in air is related to the frantic motions of molecules as they jostle and collide. Since air has a lot of empty space, the communication that a wave is coming through has to be carried by the motion of particles. For air, this motion is about 500 meter per second, but only about 350 meter per second directed in any particular direction. So let's have faster sound speeds because atoms are hooked by the string. That means there is a bonds. So don't have to rely on atoms to traverse gap. Spring compression can does travel faster than actual atom motion. So sound, what is sound intensity? Sound requires energy pushing atoms or molecules through a distance and therefore a power. Sound is characterized in decibel according to sound level. And example is this for you. We have discussed in our previous lecture. Sound hitting your eardrum. This is also we have learned in our previous lecture. This is review one. Sensitivity of the human ear. This is the actually range of hearing sound 20 hertz to 20,000. So the impressive range of 3 decades logarithmically about 10 octaves factors of 2 compare this 2 vision with less than 1 octave. This is the frequency difference between hearing level. Our speaker geometry we are using in our real life actually use the to make sound wave. Push me and pull me. Cone movement, push. This is the magnet. When the center of the speaker cone is kicked, the whole cone can't respond instantaneously. The fastest any mechanical signal can travel through a material is at the speed of sound in the material. So in this way, sound wave propagate. The looks of sound waveform, frequency content, digital sampling, all shapes of waveforms. Different instruments have different waveforms. Glockenspiel, soft piano, loud piano, trumpet. Our ears are sensitive to the detailed shape of waveforms, more waveforms. How does our ear know? Our ear pick out the frequency components of a waveform. A DC constant signal has no wiggles, thus is at zero frequency. And this is the one. A sinusoidal wave has a signal frequency associated with it. This is the faster wiggles, and the height of the spike indicates how strong amplitudes that frequency component. This is the different phase. Composite waveform. This is the description. This is the time series, Fourier expansion, and power spectrum. This is the decomposition as square wave. We have to use Fourier series to expansion of a square wave. This is the real life application of in engineering. Fourier series for k equals to 1, 5, k equals to 11, k equals to 49. The air assesses frequency content like this by waveform. Now we will discuss about actually what is Doppler effect. What is Doppler effect? We'll discuss now. So if source moves away, light appears redder than it is. If source moves towards us, light appears bluer. So visible light regions of the electromagnetic spectrum, the shift of the light waves is proportional to the relative speed of the source and the observer. This is the main properties of propagating wave. So Doppler shift, what is the Doppler shift? Wavelength is shorter when approaching and stationary wave is there in the middle. Wavelength is longer when receding, okay? When approaching and when opposite, wavelength is longer. So in laboratory spectrum, comparison of laboratory of to blue shifted object, reference lines from laboratory source and absorption lines from star. This is the reference lines from laboratory resource, absorption lines from star. Wavelength shift. What will be the wavelength shift? Assume radial speed b of glowing object is small compared to speed of light c, where the velocity is more and more less than the velocity of light. Then lambda naught is reference wavelength of medium at rest. In that case, the difference change in wavelength divided by original wavelength equals to lambda minus lambda naught divided by lambda naught equals to minus b by c. So frequency shift will be like this. Change in frequency divided by original frequency equals to f minus f naught divided by f equals to b by c. So example of calculation, the star Vega has a hydrogen line of 656.255 nanometer, which is shifted from the reference value of 656.285 nanometer. Is it moving towards us or away? Calculate its speed. Red shifted to longer wavelength, so moving away. Speed is actually minus 13.7 kilometer per second. Rotation rate from the Doppler shift. This is the slow radiation. This is the fast radiation. Slow radiation because narrow spectrum lines indicates that star A is rotating slowly, and wide spectral lines indicate that star B rotates rapidly. This is the normal curve in statistics. We learn from normal distribution. Discovery of planets around remote stars. Orbits of unseen planet. Rotation of speed galaxy from 21 centimeter spectral line atomic hydrogen. Historically, actually, Doppler shift Edwin Hubble observed that the universe is expanding. Using these properties of Doppler effect, Edwin Hubble observed that the universe is expanding. So what Hubble found, the Hubble constant is not equals to 558 kilometer per second, is the slope of this graph, and comparing this to Mason in 1931. So according to Hubble's law, velocity equals to h naught multiplied d. H naught is called the Hubble constant. It is generally believed to be sound 65 kilometer per second per MPC plus or minus about 10 kilometer per second MPC. The further away you are, the faster you are moving. So according to the Hubble. So implications of Hubble's law, distance equals to velocity divided by Hubble constant. So to get a rough idea of how far away a very distant object is from Earth, all we need to know is the object's velocity. The velocity is relatively easy for us to measure using Doppler effect or Doppler shift. Space between the galaxies expands while galaxies stay the same size. Systematic expansion. This means this expanding in a big way form. So now, what is Doppler effect? Actually, as a wave source approaching, an observer encounters waves with a higher frequency. As the wave source moves away, an observer encounters wave with a lower frequency. And the Doppler effect, this apparent change in frequency due to the motion of the source or receiver is called Doppler effect. This is the actual definition of Doppler effect. The greater the speed of the source, the greater will be the Doppler effect. Doppler effect sites we have used here. So imagine a bug jiggling its legs and the bobbing up and down the middle of the quiet pool. The crest of the wave it makes are concentric circles because the wave speed is the same in all directions. If the bug bobs in the water at a constant frequency, the wavelength will be the same for all successive waves. The frequency is the same as the bug bobbing frequency. So Doppler effect, the bug maintains the same bobbing frequency as before. However, an observer at B would encounter a higher frequency if the bug is moving towards the observer. And each wave crest has a shorter distance to travel, so they arrive more frequently. Each crest has to travel further than the one ahead of it due to the bug's motion. So this is the due to Doppler effect. Now, another example of Doppler effect, sound. The Doppler effect causes the change in pitch of a siren. When a fire truck approaches, the pitch sound higher than normal because the sound wave crest arrive more frequently. When the fire truck passes and moves away, you hear a drop in pitch because the wave crest are arriving less frequently. So this is the example. The change in loudness is not the Doppler effect. It is the shift in frequency. Okay, you have to remember this one. The police use the Doppler effect to radar waves to measure the speed of cars on the highway. And radar waves are electromagnetic wave. Police bounce them off moving cars. A computer built into the radar system compares the frequency of the radar with the frequency of the reflected waves to find the speed of the car. This is the actually police using radar wave from, and reflected waves are shorter. Bats hunt moths in darkness by echo location and the Doppler effect. Some moths are protected by thick covering of a fuzzy scales that deaden the echoes. This is the real example of Doppler effect. In light, the Doppler effect also occurs for light. When a light source approaches, there is an increase in its measured frequency. When it recedes, there are a decrease in its frequency. When a source moves towards you, do you measure an increase or decrease in wave speed? You must know about these incidents. Neither, it is the frequency of a wave that undergoes a change, not the wave speed. So how does the apparent frequency of wave changes as a wave source moves? Now we'll discuss when observer is at rest and source in motion. When the source when the source moves towards the stationary observer, suppose a source S is producing sound of pitch n frequency and wavelength lambda, then the velocity of sound is b. Let the source move with a velocity a towards the observer in 1 second, and waves will be continued at a length b minus a. This is the actually, and waves will be contained in length b minus a. Actually, as distance equals to velocity multiply time, but in 1 second, distance equals to velocity. This is why b minus a length. And apparent wavelength will be velocity, apparent velocity divided by frequency b, from b equals to f lambda. This apparent pitch will be apparent frequency equals to b divided by lambda dash. So apparent frequency equals to, putting the value of lambda dash from here. So we get n dash equal to b minus a into n. Thus the apparent pitch of the note increases when the source moves towards the stationary observer. This is the actually example. This is the velocity, this is the source, and this is the observer. When source moving towards the observer, then velocity become b minus a in 1 second. Now when the source moves away from the stationary observer, suppose a source S is producing a sound of pitch n, that means frequency n and wavelength lambda, the velocity of sound is b. So let the source move with a velocity away from the observer in 1 second, and waves will be contained in a length b plus a, because in 1 second distance equals to velocity multiply time. So distance equals to velocity multiply 1. This is why this is the distance. And the apparent wavelength will become lambda dash equals to b plus a divided by n, using b equal to f lambda. So lambda equals to what? Lambda equals to b by n. That, but apparent velocity b plus a. This is why. Now this is the when source moves away from the observer. Okay, this is the source moves away from the observer. This whole distance is b, okay, in 1 second. But after moving away from observer, the distance is b plus a in 1 second. Okay, distance equals to velocity multiply time. This is why velocity multiply 1. This is why b plus a distance. So apparent pitch will be n dash equals to b by lambda dash. Just putting apparent pitch will be b divided by b plus a into n. So thus the apparent pitch of the note decreases when the source moves away from the stationary observer. More for the same values of BA and the values of n dash in equation 1 will be different. Again, another condition, when the observer moves towards a stationary source, that means source at rest and observer in motion, the number opposite to the first one. So suppose a source as is producing a sound of pitch and wavelength lambda, the sound of velocity b, let the observer moves with a velocity b towards the stationary source. In this case, the observer receives more number of waves in 1 second. The apparent wavelength will be n plus b by lambda. Okay. So this is the source and this is the observer, and their length will be at time 1 second b. But after moving if the observer moving away from the source, then distance will be shorter. So in this case, apparent pitch will be b by lambda plus small b by lambda. So n dash will be this, and but b equals to f lambda, that means n lambda. So lambda equals to b by n. Putting the values, we get this. Thus the apparent pitch of the note increases when the observer moves towards the stationary source. Now second part, when the observer moves away from a stationary source will be a stationary. Suppose a source S is producing a sound of pitch n and wavelength lambda, and the velocity of sound is v. Let the observer moves with the velocity b away. This is the source and this is the observer. So their distance will be b in 1 second. But if the observer moves away from the stationary source, then this will be the figure for that. Now from the stationary source, in this case, the observer receives less number of waves in 1 second. This is why the apparent wavelength remains the same. The apparent frequency will be n dash equals to n minus b by lambda. B is the actually length in 1 second while the moving away from the source. So n dash equals to b minus lambda divided by b minus lambda. So n dash equals to b minus b divided by lambda. But using lambda equals to b by n, we get this. So from equation 2, we get the apparent pitch of the note decreases when the observer moves away from a stationary source. Now, when both the source and the observer are in motion, when the source moves towards the observer and the observer moves away from the source. Suppose both are moving. Suppose a source S is producing sound of pitch n and wavelength lambda. The velocity of sound is v. The velocity of the source is a and the velocity of the observer is b. In this case, let the source move towards the observer with a velocity a and the observer move away from the source with a velocity v. The apparent wavelength will be lambda dash equals to b minus a by n. So this is the source and this is the observer. Their distance in 1 second is b s equal to bt, s equal to b velocity multiply 1. This is why velocity equals to distance. Now if source moves towards the observer and observer moves away from the source by b length, and this is the length. So apparent pitch will be b minus b by lambda dash, and in this way n dash equals to b minus b, lambda dash equals to, putting the value of lambda dash, we get this one. So special case from equation 1, when the source and observer move towards each other. In one, taking b to be negative because opposite of previous condition, b minus b plus b divided by this. When the source and observer move away from each other, just taking a negative, we get the condition. And dash equals to b minus b divided by plus. Source moving away from the observer and the observer moving towards the source. In the equation, taking both a and b is negative, we get the condition. Now effect of wind velocity. Suppose the wind is moving with a velocity w in the direction of propagation of sound. The apparent velocity of sound will be b plus w. In all relations, in place of b, if we put b plus w should be used if the wind is blowing in direction, and the velocity of sound will be b minus w when if the wind blowing in the direction opposite to the direction of propagation of sound, we have to use b minus w in place of b. The general relation of apparent pitch will be this, b minus b divided by b plus. So Doppler effect in light we have discussed in our previous slide. This is the application, velocity and rotation of the sun, discovery of double stars, redshift. This is the application. Saturn's ring is due to the Doppler effect. I will discuss some real life example. A motor car sounding a horn at a frequency of 100 Hertz moves away from a stationary observer towards a rigid flat wall with a velocity of 36 km per hour how many beats per second will be heard by the observer? The velocity of sound in air is 350 meter per second. The given condition is b equals to 350, a equals 36 kilometer per hour, that means 10 meter per second, and frequency will be 100 hertz. Here the observer receives sound of apparent frequency n1 from the moving source directly, and also sound of apparent frequency n2 from the sound waves reflected from the wall. So n1 equals to n into b plus b divided by b plus a. Just putting the values, we get n1 equals to 97.23 hertz, and n2 equals to, we get 102.9 hertz. Number of beats will be n2 minus n1 equals to 5.67. The apparent frequency of a whistle of an engine changes in the ratio 6:5 as the engine passes a stationary observer. If the velocity of sound is 352 meter per second, calculate the velocity of the engine. When the source moves towards the stationary observer, this. When the source moves away from the observer, then B plus A. This may be A. So dividing by 1 by 2, we get, this is actually wrong, 20 mistake. This will be A. B plus A divided by B minus A. We get the result. Now another example, two trains traveling in opposite direction at 100 km per hour each cross each other while one of them is whistling of the frequency of the note is 800 hertz. Find the apparent pitch as heard by an observer in the other train. So before the train cross each other and after the train have crossed each other, what will be the apparent pitch? So velocity of sound given 340 meter per second. Here 340, I equals to 100 kilometer per hour, that means 250 by 9 meter per second, and b equals to 250 by 9 meter per second, n equals to 800 hertz. In the first case, the source and the observer are moving towards each other. Therefore, n dash equals to n into, n means frequency here, b plus b divided by b minus a. N dash equals to, just putting all the values here, we get this. In the second part, in the case, the source and observer are moving away from each other, just opposite of this equation. Okay, here plus minus, but we have to use minus plus, just opposite. Putting all the values, we get the result. Now another example, same example. Calculate the actual frequency of the note given by the whistle. Velocity of sound is this. We have to find out the n. N1 minus n2 equals to 500. N1 is the apparent pitch when the train is approaching the observer, and n2 is the apparent pitch when the train is moving away from the observer. So we get the equation, and this. Another example, a person is standing on a railway platform. An engine, while approaching the platform, blows a whistle of pitch 660 hertz. The speed of engine is 72 km per hour. Velocity of sound 350 meter per second. Calculate apparent pitch of the whistle as heard by the person. Velocity would be this, and a equals to 20 meter per second. So if the source is moving away from a stationary observer, we must know about this. Apparent pitch will be b divided by b minus a n, just putting all the values. Similar example, when the source moving away from a stationary observer, b plus a. Calculate the actual frequency of the whistle. The source is moving towards a stationary observer. Similar example. Both are moving, the source and observer are moving towards each other. Two aeroplanes A and B are moving away from the another with a speed of 720 km per hour. The frequency of the whistle emitted by A is 1100 hertz. Calculate the apparent frequency of the whistle as heard by the passenger of the aeroplane B. velocity of sound is this 350. Since the source and observer are moving away from one another, this is why using this formula. Similar example, and this is also similar one. This is left for you. Number of beats are heard by A n minus m2. Motor car find, calculate the difference in the frequencies of the notes heard by him. When the source is at rest and the observer is moving towards the source, show that the moving observer will receive a wave whose apparent frequency f naught is given by this, where f equals to actual frequency of the wave emitted by the source and b is the velocity of the wave through the medium of which is at rest. V naught is the velocity of the observer towards the source with respect to the medium. B, what will happen when the observer is moving away from the source? The source observer is moving with the velocity v naught towards the stationary source S. Then the source S is emitting wave which are traveling through the medium velocity b. Suppose V is the observer and S is the source, and observer is moving towards the source with a velocity v naught. So in this case, we know v equals to f lambda, where lambda is the wavelength of the wave and the distance between the adjacent crest. If the observer were at rest, he would have received f number of crest in unit time. So since the observer is moving towards the source, he will receive more number of crest in unit time. The increase in the number of crest received by the observer in unit time is b naught by lambda. Therefore, apparent frequency will be original frequency plus this apparent frequency b naught by lambda. So we get the proof. Now, second part, when the observer is moving away from the source, apparent frequency as received by the observer is f naught equals to f minus b naught by lambda. Now, when observer is at rest, the source is in motion towards the observer, show that the apparent frequency will be this. Similarly, when the source is at rest, the successive wave crest emitted by it are one wavelength lambda apart. When the source is moving towards the observer, the distance between adjacent crest is decreased. By the time the source travels in one cycle, time taken in one cycle is 1 by f. The distance traveled was by the source in the cycle is bs by f. Thus, the apparent wavelength for the source will be lambda s is given by lambda s equals to lambda minus bs by f. So frequency of the source will be b by lambda s equals to this. Similarly, we get the second part. show that the Doppler effect is greater when the source approaches a stationary observer than when the observer approaches the stationary source with the same velocity. When the source approaches the stationary observer with the velocity Bs, the apparent frequency is this. When the observer approaches the stationary source with the velocity Bs, then the apparent frequency will be this. Now, difference between these apparent four frequencies is this. So, you from this equation, you must have source frequency greater than observed frequency. This is another application. This is another one. This is left for you. This is the another example of Doppler effect. This is the supplementary problem for you. So from this lecture, we have studied actually what is Doppler effect. The Doppler effect occurs when a source of sound is moving with respect to the observer. A source moving towards an observer appears to have a higher frequency and the shorter wavelength. A source moving away from an observer appears to have a lower frequency and longer wavelength. Remember it. So this is the at rest and fire truck moving towards the source. In that case, if the source here and distance equals to d equals to lambda, source fixed, if we can figure out what the change in the wavelength is, we also may know the change in the frequency. When the source is approaching, the observed wavelength is shorter. So lambda dash equals to lambda minus velocity of source. So then the observed frequency will be f dash b by lambda dash. B equals to f lambda, we know. Now the change in the frequency is given by f dash equals to f by 1 minus source velocity, source approaching higher than frequency. And similarly, the source is moving away from the observer. We get this. So if the observer is moving with respect to the source, things are a bit different. The wavelength remains the same, but the wave speed is different for the observer. So this one, change velocity goes to velocity plus velocity of observer when the observer is approaching. So in that case, pitch or frequency, apparent frequency will be this. For an observer moving towards a stationary source, this one. And if the observer is moving away, just minus. Here plus and here minus. This is the example of you. Example. All four equations are in the Doppler effect can be combined into one. You just keep to mind that back of the sign. Approaching means higher frequency, apparent frequency greater than f, and receding lower frequency. Apparent frequency will be less than the original frequency. So thanks to everybody, and okay, bye for today.